Hello students, welcome back. We are going to continue with the topics of CMOS inverter. In the last lecture, we have derived the expression for the switching voltage threshold, that is VTH, of CMOS inverter. So today we are going to take this further. So we will do noise margin analysis now of the CMOS inverter. Noise margin analysis. So earlier, you remember we have defined four critical parameters. One of the critical parameters VTH is over. We have defined VOH, VOL, VIH, and VIL of the of the resistive load inverter in general, right? We have seen the definitions also. So noise margin analysis means ability of the CMOS inverter to distinguish between actual signal and noise signal, or how immune is my CMOS inverter to the noise, whether it's getting affected or no. So let's recap a little bit of a concept for the first 10 minutes and then we'll switch over the topic. Alright, so let me begin with this. Little bit of concept now. First I'll try to cover and then I'll go to the actual topic now. Okay, so let me take a CMOS inverter. So it consists of a NMOS, a PMOS. Its gate terminal are tied together. Here we apply the input. Here is my VDD, this is my ground, and this is my Vout. Alright, now if I check its VTC curve, it looks something like this. So we have very well have defined three regions perfectly well. So what are those three regions? Can you help me out? So if this is my CMOS inverter, ideally how it should be? Ideally the CMOS inverter should look something like this. Its VTC curve. Correct? But practically its VTC curve is something like this. Yes or no? And here we have defined three regions of operation. First is this point, mostly. Then we have this point, region A, region E, and region C we have defined. So this was V in less than VTOP. So my NMOS is cut off. Here it's VDD plus VTOP. So whenever V in is greater than VDD plus VTOP, my PMOS turns off. This is still VDD. Okay. So this region number 1, I call it region number A. This is region number E. Okay. And somewhere around here at there is one more curve. If I take this as V in equal to V out curve, which is equal to VTH, this point somewhere around, if we extend it down, this point is called as threshold voltage of the CMOS inverter. And for a very brief range, this region we can call it as region number C. Yes, this very brief region compared to this, we have region number C. We are not defining it now, right now. So this we are calling it as region number C, near this switching threshold. So A, we have NMOS off, E we have PMOS off, and C both are on. This is properly defined. Okay. So now, if I say, if you only consider, the ideal inverter, if you consider the ideal VTC curve, where is the ideal VTC curve? This one. Let me mark it over here. The dotted line in the center, right? Here, this one. So, yeah, middle में. Okay. So for ideal VTC curve, what can we write? If V in is less than VTH, my input is logic 0. Okay. And what is my output? My output is logic 1. Correct? Whenever Vin is greater than VTH, this is for ideal inverter, huh? For ideal VTC or ideal inverter, CMOS inverter. So if Vin is greater than VTH, my Vin is logic 1 and my Vout is logic 0. So ideal VTC curve, let me just show it over here like this. It is somewhat over here, right? This one. This is VTH and this is Vout, this is VDD. So whenever Vin is less than VTH, input is logic 0, output is logic 1. Whenever Vin is greater than VTH, Vin is logic 1 and output is logic 0. It's straightforward, but it's not straightforward as we come over here in the CMOS inverter. In a CMOS inverter, now let's come to region number A. Let's say here if the noise comes and enter in region number A, you know, let's say we are consider 1 point over here and noise enters the system in region number A point, this point Vin. So it can enter from Vin, right? So let's say noise has come and entered this region. Let me have drawn an exaggerated version. So this is my, let's say, noise signal. It has entered the region number A. Will it affect the region number A? Can you tell me? Will it affect region number A? Yes or no? Will this noise affect my region number A? Answer is, your response should be yes or no. That's it. With reasoning. Will the noise affect my operation of CMOS inverter in region number A? Yes or no? Yeah? What do you think? See, noise can enter in both the, let's say it is over here. Input is changing from 0 to 1. So noise can affect this system, right? It can override this signal. It can override this signal. Yes or no? So noise can affect my logic 0 and logic 1 also. So let's say my input is logic 0 and it's affecting in region number A. Will it affect over here? No. Why? Because in region A, what is my dV out by dV in? As you can see, my dV out, my dV in is fairly constant. So output is constant. So derivative of a constant is 0. So my gain, this is nothing but my gain. So noise requires some amplification for it to, affect the system. Here my gain is 0. So it will not at all affect this system at all in region number A. Same is the case with region number C, E. So let's say if the noise comes here and enters the system like this. So will it affect the system? No. In region number E also we have dV out. The gain of the system is 0. The gain of the system is 0. So in region number A, dV out by dV in is 0. Agree? And region number E also, dV out by dV in, that is the gain, is 0. Yes or no? What about in region number C? If the noise comes and affect region number C, what will happen? Or what should happen? And what is the, this is region C, VTH. Let's say if noise comes and enters the system, what will happen now? Will the noise gets amplified? Yes. In region number A and E, what is happening? In region number A and region number E, noise is getting attenuated because the gain of the system is 0. In region number C, this is region C. As you can see, in region number C, the gain of the system, let's say if you consider ideal inverter, the slope of this vertical line, is infinite. So here in region number C, dV out by dV in is very high. So we mean to say the gain is very high, meaning if your signal falls in region number C, which is very small, it will amplify. So here in region number C, the dV out by dV in is not 0. It's actually greater than 0 actually. So gain is not at all 0. So here the noise will get amplified in region C. Yes, noise gets amplified. I mean amplified to the suitable level such that it changes the logic level. Let's say it was supposed to be read as logic 0, it is reading now as logic 1. Let's say the output is supposed to be logic 1, it's now at logic 0, because amplification happens in the region number C. So you should never ever have any number in region number C, either input or output. You should avoid region number C. Okay, so in region number C we have the maximum gain. Yes or no? So how do you define a robust CMOS inverter? Very robust CMOS inverter. A robust CMOS inverter is immune to noise, in steady state conditions. When the signals are not changing, when the signals are changing, let's a different story. But in steady state conditions, your noise must get cancelled, must get killed. Okay, so first of all, in region number C, it should not fall. It's a very small range, but still it should not fall. Now, can you tell me how else we have to define two more boundaries now for region B and D? How will I define those boundaries? Can you tell me how? You already know the answer. What should be my dV out by dV in such that my noise cancels out? Yeah, you have guessed it correctly. We have already have discussed this before. The noise will cancel out when at 2 points. Where? Can you tell me? We have done this before. Tell me fast. Whenever my dV out by dV in is what? -1. Yes or no? So where dV out by dV in is -1. -1, of course, it will get not amplified, it will get attenuated. So these are the two additional points. This is called as VIL, and this point over here where again the noise dV out by dV in is equal to -1. This is called as VIH. So these are the 2 points which will define the boundary. So this becomes my region number B, and this becomes my region number D. Okay, so these are the two boundaries. Let me just if you want, I can draw it again. I hope you are following this now. So whenever this is not 1, actually equal to -1, dV out by dV in equal to -1. So whenever the gain becomes -1, it will not attenuate, it will not amplify the noise, it will attenuate the noise. So in region number B and D, at this VIL and VIH points, my noise margin levels, my noise will get definitely attenuated. Okay, just attenuated, it will not get this. So here the gain of the system is -1. Okay, agree? So again, let's recap. In region number A, the gain is 0. Region number E, the gain is 0. Region number C, the gain is maximum. So you should avoid getting any number in this range, or else we cannot determine the state of the system. Okay. Region number B and D, at these 2 points VIH and VIL, that is the critical parameters, my gain of the system is -1. So noise will get attenuated in region number B and D also. Alright, now let me draw a clean VTC curve. If I draw a VTC curve now, and I only concentrate on showing you all drawing the here it is. Now let me only show you all that 2 points on the curve. Here it is. This is VIL, this is VIH. Okay, and these 2 points, my dV out by dV in should be -1 here also. Okay, so these are the two boundaries of the system. Now there are two more added. So here it is 1, here it is 1, this is VTO N, this is VDD plus VTO P, this is VDD. So these are the boundaries. So this is region number A, B. Between VIH and VIL it should not fall. So this is region number C. Okay, VIH to VDD plus VTOP, region number D, and then VDD plus VTOP to VDD, it is region number E. Okay, so now the new noise margin will be according to this. If, let me write, this is important point. Now here I can say and make an important statement over here, that is, if Vin is greater than VIH, input is logic 1, correct? If Vin is less than VIH, input is logic 0. So I have defined these boundaries now. Alright, and what is my undetermined state? Whenever my input falls between or equal to VIH, less than VIH and greater than VIL. So this state I cannot allow my input to enter. This is called as indeterminate state. Undeterminate state. We cannot determine the actual logic level. Indeterminate region. Okay, I should never ever allow my input to fall in this range. If my input ever falls within VIL and VIH, I can never actually determine the actual state of the system, because in this region the gain of the system is pretty high. Okay, here the output is falling rapidly with respect to input, so we never know your immunity level, the noise immunity will be very much be challenged when you go in this range. So goal of any inverter or a CMOS inverter should be to reduce the gap between VIH and VIL, okay, of the inverter. Alright, now for this we defined, you know now how to find VIH and VIL. Now for this we have noise margin levels now. So noise margin levels will be, can you tell me what will be the formula for noise margin high and low? We have done this for resistive load. Come on. What is the formula for noise margin high? For low it is VIL minus VOL, and noise margin high is VOH minus VIH. So in order to determine noise margin levels, we have to, okay, sorry for that, yeah. So in order to determine noise margin high and noise margin low, these are noise margin levels. Okay, so in order to determine that, we have to first determine VIH, VOL, VOH and VIL for a CMOS inverter. So let's start with the derivation straight away. Okay, VIH we have already studied. Now let us concentrate and start with the derivations for these 4 parameters. Actually we have to derive for only 2, because for VOH and VOL it's very simple, it will complete within 2 minutes. Let's start with, so let's write down first. I hope the objective is clear. We have to find 4 critical voltages. So first let's start with region A in the VTC curve, which is also called as V less than VTON, or we can say that we are finding to find VOH. So this is the, we have to find VOH. Okay, Now we know this is the VTC curve, right? Let me again and again and again draw this to highlight the fact and its importance. Okay, where is my region number A? This is VTO end. This is the line that is defining V in. This is V out. Okay, so in this region, this is region A. So whenever V in is less than VTO end, what will happen? Can you tell me? Come on. Which transistor is off, which is on? We have done this many times now. Today I've repeated the same thing 4 times. Region number A. Tell me. So let's write down. In region A, where Vin is less than VTON, Vin is same as VGSN. So VGS is less than VTON. That means my NMOS will be in cutoff mode of operation, and we have seen that PMOS is in linear linear mode. So therefore, if I ever draw my CMOS inverter, how will it look like? Let's say I replace the this is my CMOS inverter, this is VDD, this is V in, this is V out. So for a V in less than VTO N, that means this is almost close to 0. So my output should be close to 1, and it is close to 1 basically. So my NMOS transistor is on, sorry, my PMOS transistor is on and my NMOS transistor is off. Basically this is the situation. Okay, so we replace the MOSFETs by their switches, by the equivalent resistance and switches. Here it is. So this is the equivalent resistance of PMOS, RP, and this is a switch opens, this is a closed switch basically. This is V out, and here we have RN, and this is open switch because NMOS is off, cut off. As you can see, my output will be pulled up towards VDD level straight away. Okay, so output goes to VDD. So here we can say that next point, please write along with me. Therefore, output V out is pulled up to VDD. Therefore, output is equal to VDD. And what is output here defined? We are defining VOH. So that is VOH is equal to VDD. So that is the derivation for VOH. I hope it is clear. So VOH is just equal to VDD. Yes or no? Agree? Is this point understood, everyone? Let me highlight that point. Yeah. Region number A. Okay. Now we'll go to region number E in the curve. Is this completed? Yes, no? Now we'll go to region number E. Region E, which is defined by Vin greater than VDD plus VTOP. Or we are finding the expression for VOL. So here is my VOH. Here it is. VOH, which is equal to VDD. Okay. So VOH is equal to VDD. Now in region number E, what is the scenario? if I plot the VTC curve, V in versus V out, my curve will be like this. Here, this is the point VDD plus VTOP, and here it is 0. So as you can see, the output is 0 almost. Okay, so at V in equal to, we can say at V in almost equal to VDD, what can you say? VGSN is VDD. And what about VGSP, which is V in minus VDD? It is almost equal to 0. Yes or no? So whenever VGSP becomes 0, my PMOS is in cutoff mode of operation. Of course, by the way, the NMOS is still on, NMOS transistor is still on, but it doesn't matter, because if one transistor is off, the current flowing has to be 0. So let me connect my writing pad properly. Yeah. So this means that my NMOS is on. Okay, VGS is greater than VTN, or this is actually equal to VDD. Yes or no? So we can write this is point A, point B in region E with V in greater than VDD plus VTOP. Remember, VTOP is a negative number, so VDD minus, let's say VTOP is minus 1, VDD is 5, so it will be V in greater than 5 minus 1, that is 4 volt. Your PMOS transistor is in cutoff mode and NMOS is in linear. How? See, first of all, VGS is greater than VTON. Yes, true, because VGSN is almost equal to VDD. Secondly, what about VDSN? That is equal to output. Output is almost 0 over here. So VDSN is actually less than VGSN minus VTSN. Okay? Yes or no? So let's say this VTON is 1 volt. Alright, VGSN is around 5. This is around 5. So definitely this is 0. This has to be less. So this is the condition when for the linear mode of operation for the NMOS. So in region number E, PMOS is in cutoff, NMOS is in linear region. Okay, so if we draw the equivalent inverter now with the switches, so these are the resistance associated with NMOS and PMOS. This is my output. So PMOS is becoming off, NMOS is on still, so it's a closed switch. This is a switch, and this is open switch. So what will happen? Output will be pulled down towards 0 level. Okay, so output will be pulled down to the ground in this case. So C point is, therefore the output V out is pulled down to ground level. So therefore we can say output is equal to 0, and here output is nothing but VOL point, and that is 0. So VOL of a CMOS inverter is 0. Therefore we can conclude that. Let me put it inside the box for you all to remember. Okay, so this is the region number, let me mark over here in this curve. This is what I'm talking about, VOL. So VOL is over here, this is 0 for a CMOS inverter. Okay, VOH was right at the top here, which was equal to VDD, and VOL is 0 for a CMOS inverter. That is what we have seen. Okay, so region number A and E done. Region number C we have already found out in the last class, the switching threshold expression. Yes or no? So are you understanding this, everyone? Just a heads up. Yes or no? Little bit you're following? Okay, yeah, Thank you. So I'll go to region number A, C and E is over. Now we'll go to B. This is the third one. This is region B, or we can say is the calculation of critical parameter VIL. Now where is VIL? Let me show it to you. So this is again, we have drawn VTC curve almost before the every answer. So let me draw it one more time. It's going down like this and staying over here. So where is this point? It's slightly here, right? Here. Correspondingly, this point is slightly below VDD. Agree? This point. And this point is correspondingly called as VIH. VIL. That is what we need to find out. So correspondingly here, my output is just below this level. Output is just below VDD, almost at VDD level, right? When my Vin is equal to VIL, my output is just below VDD. Do you agree or no? Yes. So let's write it down step by step. At Vin equal to VIL, the output Vout is slightly just below VDD level. Okay, therefore I can say over here, what is my here we can say Vout is almost equal to VDD, but not equal to, almost equal to VDD, right? So what can you say about VDSN? VDSN is VDD, right? Because almost is equal to Vout. And what about VDSP? Remember VDSP was given by Vout minus VDD. That is becoming 0, almost close to 0. Yes or no? Because Vout is VDD now. So here VDSN for the NMOS transistor. Let's come to the NMOS transistor. Okay. For the NMOS transistor, my VDSN is almost equal to VDD. So VDSN should be greater than VGSN minus VTON. Let's consider this is 1 volt. VGSN is around VIL, and let's say VIL is somewhere close to around 2 volt. Let's consider it 2 volt. Okay, and what about VDSN? This is at 5. VDD is 5 volt. This is at 5. So definitely this is greater. So NMOS is in saturation. What about PMOS transistor? My PMOS transistor VDSP is almost around 0. So VDSP, is it greater or less? VGSP minus VTOP. VGSP is what? It's Vin minus VDD. Okay, this is around minus 1. This is 5. Vin over here is VIL, that is 2 volt. So this is around minus 3. Okay, and this VDSP, it's around close to 0. Okay, okay, so what it is, this is around minus 3, minus 3 plus 1, so minus 2. So 0 greater than. So that means PMOS transistor is in linear region. Yes? Oh, sorry for that. This is in saturation. NMOS is in saturation and PMOS is in linear region. Are you understanding? Yes or no? In region number B, do you agree on that? I've used numbers and explained you all. You can check it out yourself. Yes. So now listen to the wordings. As my input voltage is increased beyond VTON in region number B, here it is. Let's say this is my point VTON here. As input is increased beyond VTON in region number B, NMOS starts conducting in saturation mode and output begins to fall. Here it is. Output is slightly falling down. Also, the critical parameter dV out by dV in, that is at VIL, corresponds to dV out by dV in equal to -1, is located in within region number B. So this is my region number B. This is A, this is B, which we are talking about. So as my input goes into region number B, my NMOS goes into saturation, PMOS goes into linear, and my output slightly falls below VDD level. Okay, and at critical parameter, that is VIL, my dV out by dV in should be equal to -1. Alright, so let's apply the KCL to the CMOS inverter. So applying KCL, what do we get? Let me, this point is B. Yeah, so we can write IDP. PMOS is in linear region, right? IDP linear is equal to, this is mod of IDP linear is equal to IDN, which is in saturation. So identifying the region of operation is very important. Okay, here in this case NMOS is in saturation and PMOS is in linear region, so please note it down. Now ID linear, we are assuming that lambda n is equal to lambda p is equal to 0, no channel end modulation parameter. So what is the equation of linear region for drain current? Here it is for IDP, it is Kp, this, let's say statement number, we will call this as 1 now, the statement. So Kp by 2 twice, okay, let me yeah, please write down along with me. So what's the equation? Kp by 2 twice VGSP minus VTOP into VDSP minus VDSP square. This is ID linear, and ID sat is what? Kn by 2 VGSN minus VTON square. Why we are writing N here? To indicate it's a NMOS transistor, and P we have written to indicate it's a PMOS transistor. This is square. Now we have to solve this and also assume that, one more thing we have to assume. What is that? Let, okay, the pen is giving me a little bit of trouble. Let me change the chord of my pen tablet. Just a second. One second. I'll just be back in a few seconds. Okay. So I got the chord and I'm changing the chord for my writing pad. Let's hope so it will work now. It's my pen. Yeah. So let's continue the derivation. So we are assuming now, let ratio be Kn by Kp. Okay. So now we'll write the second statement over here. So here it will be twice. What is VGS and VGSP? Remember, these are the constraints which we have to remember. VGSP is V in minus VDD. VDSP is V out minus VDD. VGSN is V in. We have written this many times. VDSN is V out. So we have to substitute it over here. So this will become 2 and 2 will get cancelled first of all. What happened? Someone has written something. So you are not audible. Now I am audible. Hello. Can you speak? Sorry. Now I am audible. Yes. Oh, sorry. I am back. What I was saying that I repeat myself. Now I am audible, na? Can you please confirm? Okay. So what I was saying was 2 and 2 will get cancelled from both the sides. These are the constraints which I have to remember every time. This comes from the circuit diagram. And we let inverter ratio be equal to Kn by Kp. And now we'll proceed forward with the derivation. Alright. And we have to substitute these terms. Instead of VGSP, VDSP, VDSP, VGSN and all these things. Okay, so let's substitute that. So here I will get twice. Let me use black color. Twice. Instead of VGSP I'll write V in minus VDD minus VTOP as it is. Then instead of VDSP I'll write V out minus VDD, and here it will be V out minus VDD square is equal to KR times KR will come over here into V in minus VTON the whole square. I hope it is clear now. So this term is this term, VDSP is over here and VDSP is over here. I hope it is clear. Okay. Yeah, let me call this equation as equation number 2.1. Okay, this equation is very handy. It will come into existence later on, but let me box it with yellow color. Just by equating IDP linear to IDN saturation. That's it, nothing else. And equating. Now, next step is differentiate this equation number 2.1 with respect to V in. But why are we doing that? Because we want dV out by dV in, and we impose the condition equal to -1. Alright. So that's why we are differentiating this with respect to V out. Now see, all the terms we have V in and V out only in equation number 2.1 if you see carefully. So we, by differentiating, we get V out is the differentiation term. Rest everything will be as it is. So it will be twice. Here is the multiplication, differentiation by multiplication. So it is twice V out minus VDD plus twice V in minus VDD minus VTOP dV out by dV in, because it is V in over here. Alright, so once it will come minus twice, here it is x square, so differentiation will be minus 2x, so minus twice dv V out minus VDD into dV out by dV in, and that is equal to that is equal to twice KR. Okay, here KR terms will come. No, twice KR V in minus VTO n. Okay, because it is dV out by dV in. So if we differentiate with respect to V in, it will be twice KR will come over here, and dV in, actually here I should have written dV in by dV in, that is 1 only. So that's why I'm not writing it over here. It's into 1. Okay. Here V out term is there, that's why we have written dV out by dV in. Here also dV out by dV in. I hope it is clear now. This expression is clear. Yes or no? Now what we will do is we'll set what we have to do. Wherever we have to reduce the noise increase the noise immunity, right? So we set dV out by dV in equal to -1 wherever it is. First of all, we can divide the entire right hand side and left hand side by 2, divide by 2, and then also we can have this -1. So we can write here nicely. Of course, this will be V out minus VDD minus V in minus VDD minus VTOP minus this 2 will we have divided. So we have divided LHS and RHS by 2 and set this and this. So this will be V out minus VDD equal to KR times V in minus VTON. So there are two terms. This becomes twice, right? V out minus VDD. Here also we have. This will become sorry. One more thing. This is -2. This we are substituting -1, right? Instead of this, we are substituting here -1. So this will become plus, right? Yeah, plus. So and 2 is gone from all this, from both the sides. So this will become plus. So we have twice V out minus VDD. Agree? Twice. Correct me if I am wrong somewhere. Then minus V in minus VDD minus VTOP is equal to KR V in minus VTON. Understood up till equation number 7? Yes or no? Now equation number 8, I'll club the terms of V in together. So we can write over here V in into 1 plus KR is equal to twice V out minus twice VDD. I've clubbed V in on this side and this VTON I am taken this side. You'll have minus twice VDD, twice V out plus VDD plus VTOP, and here you will have minus, no, this is minus, so this will come plus KR VTON. This is what I will get. So minus 2 VDD and VDD will become VDD. So I'll write this V in into 1 plus KR is equal to twice V out minus VDD plus VTOP plus KR into VTON. So I am solving for V in equal to VIL, right? So V, instead of V in, I'll substitute VIL, because now I'm substituting V in equal to VIL, right? So VIL is equal to, this is 1 plus twice V out minus VDD plus VTOP plus KR times VTON divided by 1 plus KR. This is the expression for VIL. Okay, this we call it 2.2. So remember, in this expression for VIL, we have one dependent term. which is V out. And where will you solve this V out from? V out will be solved from equation number 2.1. So equation number 2.1 and 2.2, you have to solve it together to get the value of VIL. So what are we doing is, I'll tell you. First let me write. So solve equations 2.1 and 2.2 together to get the value of VIL. So what they are saying is, conceptually, so if this is my VTC curve, it's falling down over here like this, and I have this point over here like this, right? This is VIL. So what they are saying is, this is VDD point. As you can see, this is slightly below VDD. So this V out, what is the value of this V out? Okay, so first of all, find out this V out, then substitute it over here. So as you can see, this will be slightly below VDD only. So maybe VDD is 5, this will be 4.8, 4.7, 4 point, if VDD is 3.3, it will be less than 3.3. So first of all, find this V out value and then substitute in this equation. Find V out value from where? From here. Yeah, solve this in terms of, we have to solve them together. Here we have to substitute V in equal to VIL. So this is V in equal to VIL. Now you have to solve for V in equal to VIL. Here, which is very important. Okay, so for finding V in equal to VIL, you have to find this V out, unknown V out value, and then put it over here and then find out the value of VIL. Okay, and what I am saying is, this V out value will be slightly below VDD level only. Okay, so this is the meaning of solving 2.1, 2.2 together. I hope the equations are clear. Now we have the last derivation for today. Can we go for region number D? Region number C we have already covered last lecture. Okay, can we start now? So we'll go for region D. This is, I think, 4.4 today. Region D. Let me open and close the PDF again. I know you have to bear with me for some more time. Just 10 to 15 minutes more. We'll complete this derivation and that will be the end of the analysis. So region number D, or we can say it's calculation for VIH point. Okay, so let me conceptually explain again. So let's say this is my VTC curve. This is V in, that's V out. That's my VTC curve. Nice and clean. Here I am taking critical parameter. This is VIH. Okay, this is what I need to find out, and this is corresponding value of V out at VIH. Okay, so now this is just after entering region C. This is region number D. Okay, I'm not marking it over here, but this is region number D. So let's start in this at V in equal to VIH. If you observe carefully, V out is slightly above 0, slightly above VOL level or 0 level, right? V out is slightly above 0. Okay, so V out is slightly above 0. Let's consider, so therefore V out is approximately equal to 0. Okay, what can you say about VDSN? VDSN is approximately equal to 0. What about VDSP? VDSP is V out minus VDD. Okay, so VDSP mod of it is approximately equal to VDD. Yes or no? Alright, so VDSN is equal to 0 means what? We can say VDSN should be VGSN minus VTON. This is 1, let's say 1 volt. This is equal to V in. So V in is VIH. Let's say VIH value is somewhere around greater than VDD by 2. So let's say 3.5 volt. Let's say for example, okay, this is 3.5. Okay, so this is 0 almost. So is this less, right? So that means my NMOS is in linear region. Agree? Because VGS is greater than VTN and VDS is less than VGSN minus VTON. Similarly over here, VDSP is around 5 volt. So what about VGSP minus VTOP? VGSP is V in minus VDD, and this is around minus 1. This V in is around 3.5. So 3.5 minus 5. So this will be around minus 1.5, and this is minus 1, and this VDSP, let's say this is around 5 volt. So this means that this is definitely greater than this value. This is around minus 0.5 and this is 5 volt. So definitely my PMOS will be in the, no, this will be mod of, so this will be less than, okay, because this will be minus 5, because this is minus VDD, right? So this will be minus 5. So minus 5 is definitely less than this value. So my PMOS transistor will be in saturation region. That is for sure. So in region number D, my NMOS is in linear region and my PMOS is in saturation region. For this we have to determine. This is the a critical parameter. So what we say over here is, so after going to region number C, where both the transistors are in saturation, output continues to fall down until it reaches a critical parameter V in equal to VIH, where the output is just above 0, and this corresponds to region number D. And this critical parameter can be found out at what point? dV out by dV in equal to minus 1. So again we have to differentiate certain equations. Let me open this document again. It's giving some trouble. Alright, so dV out by dV in is equal to minus 1 at this point. So we have to find the equation, differentiate it, and then equate dV out by dV in is equal to minus 1 for noise suppression or noise attenuation at region number D. So let's continue. So now we have determined NMOS is in linear, PMOS is in saturation. Let's proceed forward. So we say now, next step, point number 2. IDP sat mod of it is equal to IDN. We equate the two linear. Okay, we should know which PMOS is operating in saturation and NMOS is in linear. We should know we know the equations now. So we can write third ID sat equation is Kp by 2 VGSP minus VTOP the whole square. What is ID linear equation? Kn by 2 twice VGSN minus VTON into VDSN minus VDSN the whole square. Now here we are assuming that lambda channel modulation is 0. So 1 plus VDS terms, lambda VDS term is not there. So now 2 and 2 will get cancelled from both the sides. Alright. Then we assume let Kn be let Kr inverter ratio Kr be equal to Kn by Kp. Now we rewrite the terms. Okay, so also we should remember the 4 constraints. What were the constraints? VGSN is equal to V in, VDSN is equal to V out, VGSP is equal to V in minus VDD, and VDSP is equal to V out minus VDD. Okay, so substitute this over here. So first term we have Kp into VGSP is V in minus VDD minus VTOP the whole square. So Kn into twice VGSN is V in minus VTON, VDSN is V out minus V out square. So we have replaced these terms. 1, okay, over here substituted it as V in, this as V out, this as V out. Alright, so this we call this as equation number. I'll mark it in yellow color because we will be using this equation to find the value of V out. Let me call this as 2 point, or rather 3.1. Okay, now we'll solve this further. Actually, solve this further in the sense we'll differentiate this equation with respect to Vn. And why we do that? Because we want to find dV out by dV in point and then set that equal to -1. So let's do that now. Differentiating equation 3.1 with respect to Vn, we get, so let's do that very carefully. We have to differentiate this 3.1. What do we get in first term? It's twice dV in by dV in. Okay, delta V out term is not there, V out term is not there, so it will be twice. Differentiation of x square is 2x, so twice. Okay, we have not written kr term. Oh, so yeah, kr term will come over here. Okay, kn by kp. So twice d vdd minus vtop. Okay, dv in by dv in. So that is actually okay. Is equal to, there it will come kr. Remember that. Then it will be twice, your differentiation or multiplication will come, so twice V out plus twice V in minus VTON dV out minus V in, and your x square will be, V out square will be twice V out dV out by dV in. Okay, I hope I've written it correctly. And the next step, what do we do? Can you tell me? We'll set dV out by dV in term as -1. So this will be 1, this will become -1, this will become -1. So let's do that. So twice and twice, 2 here from here common, 2 here will get cancelled. Let me not cancel it over here. Okay, so I'll write it again. V in minus VDD minus VTOP, here till multiplied by 1 is equal to KR times, here 2 gets cancelled, so V out plus minus, because here it is minus, so it will be V out minus V in minus VTON. Then here it is -1, here it is minus, so it will become plus twice. Oh, 2 is gone actually, 2 we have removed it, plus V out. That's it. I hope I have done it correctly. We have set and divided LHS and RHS by 2. Okay, so this is what do we get. I hope it is correct now. So now we club the terms of V in together. So what do we get? V in, and we bring this V in together over here. So we'll have plus KR into V in is equal to, then we can club these terms, we can send it on right hand side, so it will be VDD plus VTOP plus VTON, I mean plus KR into twice V out plus VTON. I hope it is clear. This V out and this V out gets added and become twice. So this becomes V in into 1 plus KR is equal to VDD plus VTOP plus KR into twice Vout plus VTON. Okay, so this becomes V in, which is equal to VIH is VDD plus VTOP plus KR twice Vout plus VTON divided by 1 plus KR. Okay, so this we call this equation number 3.2. This will give me the value of VIH. Here it is. As the last equation, but here it is a dependent term of V out, so you have to get that value of V out from equation number 3.1 and 3.2. We have to solve it together, so we can write over here finally last point for the day: solve equation 3.1 and 3.2 together to get the value of V in equal to VIH. Alright, so this completes the derivation for all 4 or all 5 critical parameters. Okay, so here what are we saying is why we want the value of V out. So referring to this curve, as you can see, this value of V out is just above 0, very close to 0, right? So we'll find this unknown value of V out and substitute in VIH equation to get VIH. Here it is. So solve equation number 3.1 and 3.2 simultaneously to get the value of VIH. Okay, so once we get all these values, then we can find the noise margin levels. So noise margin low will be VIL minus VOL. For CMOS inverter it is 0, VIL minus 0, so it is VIL only. And noise margin high will be VOH minus VIH. And for a CMOS inverter this is VDD, so VDD minus VIH. So these are the formula for the noise margin levels for CMOS inverter. Okay, so next time we should be ready with finding solving the equations numericals on the CMOS inverter. So until then, have a good day, and that's it for today. So thank you everyone for all your patience.